Assalamu alaikum and good day to all of you, my dear students. In this tutorial we will discuss vectors in space. In vectors in space we will tackle the following objectives. First, collinear vectors. Second, coplanar vectors. Third, base in space. And finally, components of a point in space. As for the first point, collinear vectors, how can we know that two vectors are collinear? Well, two non-zero vectors u and v are collinear if we can establish graphically that the two vectors have the same direction. That is to say, they are either parallel to each other or they are on the same straight line. Or in a vector way, that is to find a vector equation between the two vectors that says u equals kv vector, where k is any non-zero real number. Finally, if you have the coordinates of the vectors u and v, we can always establish that if the ratios of x to x prime equals y to y prime and z to z prime equals to k, then again the vectors are collinear. Second point, we will tackle coplanar vectors. Well, this is new to you, so pay attention, my dear students. How can we prove that three non-zero vectors are coplanar? Well, three non-zero vectors u, v, and w are coplanar if and only if one of the vectors u, v, or w can be written as a linear combination of the other two vectors. For instance, w vector, if I can write it as a constant by a vector u added to another constant by a vector v, where the constants alpha and beta are real and non-zero, then we can say that these vectors are coplanar. Now this is a figure that shows three coplanar vectors where one of the vectors w is equal to a constant by a vector u and another constant by the vector v. We will see this later, but first we will see another way to prove that vectors are coplanar. The other way is that if we can find one of these three vectors u, v, and w to be coplanar with the second one. Example, now here we have u and v are collinear, where the third vector w, any third vector w, could be coplanar with them. What's the importance of coplanar? We'll see that later, inshallah. Now let's go to the third point now. The third point is base in space. What's a base? Now, definition. Any three non-coplanar vectors would form a base. Now, this is one thing to say about coplanar. Well, let's see. What do we mean by a base? A base, let's for instance, the non-coplanar vectors I, j, and k form a base in space. That is to say, they form this system. Okay, you know this, I and j. I is the direction vector of the x-axis, j is the directive vector of the y-axis, which is the plane that we used to, use when we needed to draw a straight line on a plane or a point, any point. Now we will upgrade our system from a plane, that is to say from two dimensions to a third dimension, which is the z-axis, which uses a third vector k. Notice that the vectors I, j, and k are non-coplanar. Again, what do we mean by non-coplanar? Non-coplanar, they are not in the same plane. The fourth point, which is components of a point in space. Now, let's see if you can do this. Can you determine the components of the points C and E and F in space? Well, here are the points. C, E, and F. Well, did you find the coordinates? Okay, if you did, then this is good for you. If you didn't, then you only have to wait to the end of the video. Now we will use a math software to see how to prove that two non-zero vectors are collinear. Do you still remember how? Okay, let's do it together. Yes, graphically. And to do this, we will consider a rectangular prism ABCD EFGH, where M and N are the respective midpoints of segment AB and segment AD. Okay, now can you say that the vectors AM and AB are collinear? Good, of course they are collinear, because we can see that M is the midpoint of segment AB and the vectors M and AB are on the same straight line. Okay, what about vectors AM and GH? Are they collinear? Yes, they are, because AM and GH are vectors on opposite edges of a rectangular prism. Okay, let's go to now the other form. Do you remember it? Of course, it's finding a vector relation between the vectors. Now let's go to the next question. Are the vectors Mn and Hg collinear? Remember that M and N are the respective midpoints of segments AB and AD. Yes, they are collinear. By midpoint theorem, we can see that Mn vector equals negative half HF vector. Well, what about these vectors? If R is any point on segment BH, notice R is nothing but a point on GH. Well, if R is any point on the segment BH, then can we say that the vectors BR and BH are collinear? Yes, again, true. Why? Because we can write it in the form of U equals KV, where K is a non-zero real number. So now we can see that we can prove two collinear vectors by two different ways, either graphically or vector-wise, in a vector form. Now what about analytically? Okay, let's find that the coordinates of BR and BH. In fact, we will see how to find the coordinates of a vector in space later on. But first, let's take for granted that they are as they are given by the software. And if you notice that the ratio of the abscisses of vectors BR and BH, the ordinates and the Z are always equal to the constant. Notice as I move point R, the ratio keeps the same. Now, my dear students, let's check coplanar vectors. As we said before, to prove three non-zero vectors u, v, and w to be coplanar, we need to find one of the three vectors to be a linear combination of the other two vectors. To do so, we will check a rectangular prism AM, AB, CD, EF, GH, where M is the midpoint of segment AB and N is any point on segment AD. Now let's see. Are the vectors AM, AN, and EG coplanar? Well, it doesn't seem that they are coplanar. In fact, they are coplanar. Why are they coplanar? Even though we can see that they are in the same plane? Because we can write vector EG as a linear combination of vector am and vector an. Let's check as we move n what happens. Still we can write vector eg as a linear combination of two vectors am and an. Okay, let's check the other case of coplanar vectors. By collinear, if I can take two vectors u and v which are non-zero to be collinear, then any third vector w will be coplanar to these two vectors. Are the vectors an, cb, and hf coplanar? ab, an, cb, and hf. Again, from this point of view, we can say that they are coplanar. But let's check something here. an and cb are on opposite edges of a rectangular prism, so they are collinear. So according to the rule, any two vectors that are collinear, then they will be coplanar with any third non-zero vector. Let's take now the vectors br, bh, and hf. Are they coplanar? Well, what if I put them like this? Of course they are coplanar, my dear friends. Why? Again, since two of them, br and bh, are collinear. Our last objective for this tutorial is to find the components of any point in space. To start with, you can notice that our system is a little bit different here. It is composed of x-axis, y-axis, and a z-axis, where the x-axis has a directed vector I, j is for the y-axis, and k for the z-axis. Now, if I need to find any point in the xz plane, here's the xz plane, then its ordinate y will be 0. And if I needed to find the components of any point in the yz plane, then its abscissa cell would be equal to 0. Finally, if I want to find the components of a point in the xy plane, then its elevation z is 0. Now, don't be confused. E, F, and G are not on the xy plane, but only the perspective here can let you see this. Now, let's start with finding the components of point E. I would like to find the coordinates or the components of point E by forming the vector starting from the origin of the system O and ending with the point E itself. Afterwards, I will try to express the vector OE in terms of the directed vectors of the x-axis I, j, and k if possible. In this case, OE vector is the sum of the two consecutive vectors OG and GE, where OG is a vector along the x-axis and which is equal to 1, 2, 3i, and GE is a vector parallel to the y-axis and it's equal to 1, 2, 3, 4, j. Now I will have OE vector be equal the components of vector OG added to the components of vector GE. As a result, the components of vector OE would be 3, 4, and 0. Okay, let's find F in case you didn't understand this. Again, we will start with finding the vector OF and expressing vector OF in terms of the director vectors of the system of axes I, j, and k if possible. But here f is in the yz plane, so there is no need for the x component here. Now we can see that OF is also formed of the two consecutive vectors OH and HF, where OH is equal to 2, 3j and 1, 2k. As a result, the components of vector OF would be 0 for the x-axis, 3 for the j component, and 2 for the f component. Finally, we'll find the components of C. C is in neither of the planes, so it will be a bit different than E and F. Again, I'll draw the vector OC and try to write OC as sum of consecutive vectors, one parallel to the abscissa axis, other parallel to the y-axis, and the third one parallel to the z-axis. OI is equal to 1, 2i, the ij, the parallel to the y-axis, equals minus j, it's in the negative sense of y, and jc in the positive sense of k, but it's equal to 1, 2, 3k. So as a result, 2 on the abscissa for OI, 0 and 0 for IJ and JC, so the abscissa of OC is 2. The ordinate of OI is 0, minus 1 for IJ, 0 for JC, so their sum is minus 1. And for the Z component, notice I didn't write 0 for the Z elevation here because OI is in the XY plane, but nevertheless it's 0. So 0 plus 0 for IJ and 3 for JC, then the result will be 3. Now OC would be 2 minus 1, 3. Hope you enjoyed this video, and hopefully I'll see you next time.